Hi, BC Calc. These are your day 122 notes. Today we are extending our concepts of polar area to look at some shaded polar areas. So we might be looking at areas that are bound by two different polar curves and determining how can we find the area between them that are contained within both. So we're going to see kind of a variety of contexts in which we might be asked to find a shaded polar area. So in order to do that, we're of course going to have to recall that from yesterday when we found polar area. It's this concept of area of a sector. So if we break up the region that we're trying to find the area of into multiple sectors, we can use the sector formula, which is 1/2 r squared theta. So the radius is going to be it's going to be f of theta, according to whatever our polar equation is, squared. And then we have d theta for all of our delta thetas along the way. So we'll integrate from theta 1 to theta 2 and be able to determine the area of that region. So if you want a picture there to re-represent that, there it is. But what we're going to look at now is the example from yesterday, where we were able to determine the area inside one of the loops of this rose curve, 6 sine 2 theta. So we're going to extend that out a little bit further and think about from determining the area inside the circle, but outside the rose curve right here. So we want sort of a shaded region that represents everything inside this circle, but outside what we have for the rose curve. So there's a polar grid for you below if you want to see if you can sketch that on your own first. You can take a moment to do that, but I'll remind you that the way this would look is the following. Look how nice that is. Wow. I have to say, I'm impressed with some of my polar curve sketching. It's not all the great, but this one's decent. Okay, so here's the circle r equals 6, right? At any given moment, the radius is 6. And then we know that r equals 6 sine 2 theta has 4 petals. So I want outside the rose curve, inside the circle, which is this red shaded region that we have here. Well, to determine that area, we're just going to use the area that we calculated yesterday to kind of get the ball rolling here today. For r equals 6, we know that shaded area is just going to be 36 pi, right? It's the area of a circle whose radius is 6. If I subtract out the area of the 4 loops of this curve, which we determined yesterday, that's going to give me the area that we have shaded in red. And that's kind of where we're headed today. So from yesterday, we determined that for all 4 loops, okay, I think one loop was just 9 pi over 2, which would make sense that if I multiply that by 4, the total area of the rose curve on the inside is 18 pi. So therefore, if I subtract those results, we get that the total shaded area of what's in red there is 18 pi. So check out yesterday's notes if you don't quite remember how we determined that area, but we're going to do more polar area practice right now. So we should be good to go in terms of hopefully recalling these concepts. Okay. So if you're good with that one, let's take a look at the very next page where it says find the area inside the smaller loop of the limicon r equals 1 plus 2 cos theta. So it says smaller loop here because if you recall, the graph of this is a loop in a loop. And this loop in a loop has a max r value of 3. And it's going to go in the direction of 0 degrees to the right because it's a positive cos equation. That's where positive cos has its max. The width of this loop in a loop is the first number here of 1. And then the opposite direction value, which is how far back in we go towards the loop, is, as if you remember, subtract these. 1 minus 2 is -1. And an r value of -1 indicates don't go away from the max, go 1 back in towards it. Now, I'm going to use a little bit of a scale here just so that we can look at this on a bigger scale, I guess. So if the max r is 3, I'm going to actually go out 6. I'm going to count every 2 concentric circles as 1 unit, okay, 1 radius length. So if we have, let's see, 1, 2, 3, 4, 5, 6. Here's where that max would be located out here. And the width of 1, the only reason I didn't like using these circles is because the width of 1 becomes pretty tiny. But if I then double that, here's now a width of 1 here. The other width would go down. And the opposite direction of -1 is going to be 2 units back in towards the max. So the way we sketch the loop in a loop is I'm going to start out here in the max. I'm going to curve around through that width, go through the pole, and then back out through this loop, right? Hit the pole again, that width, and hopefully be able to loop back around and get a pretty accurate sketch here. So we'll see how good I am at creating the sketch this time. So we're going to curve around, loop through the pole, back out like this. That's pretty good. Not bad for my loop and a loop there. Okay, so in order to determine the area inside the smaller loop, what we're looking at is this piece right here. Looking at that shaded region, okay? And as it turns out, we do have some symmetry here, right? The top half of the shaded region, the bottom half would have the same area, assuming that I drew that correctly to scale. So using the symmetry, because there will be a ton of symmetry, of course, within our polar curves, let's just do 2 times the area of that top half of the polar curve. Okay, so what we have to figure out right now is the area is, of course, 1/2 integral from theta 1 to theta 2 of half of theta squared d theta. We have to figure out what are theta 1 and theta 2 that get you these endpoints for the area that we're going to be integrating along. Well, to figure this out, what we're going to do is we're going to set our equation right here equal to find the angles for theta. In one case, we're going to set it equal to r equals 0. That's the r value at this endpoint. And the r value at this point, endpoint over here, is r equals -1. So to find these two values of theta, in one instance, we're going to solve where does 2 cos theta plus 1 equals 0. Okay, that's going to get me the first angle right here. And then as I loop around, the second angle is when 2 cos theta plus 1 is equal to -1. Okay, let's see if we can use that to determine the bounds of integration. So we're going to get cos theta equals -1/2 here. Over here, if I subtract 1, 2 cos theta would equal -2, and therefore cos theta equals -1. So cos theta equals -1 when theta is pi, right? You can think about the cosine curve, unit, circle, whatever you need there. Cos theta equals -1/2. If you don't quite recall, you can set up a triangle here. Cosine's negative in quadrant 2 and quadrant 3. But I'm looking for this first angle when this is true, and that first angle across from radical 3 would be that theta equals 2 pi over 3, right? Reference here is pi over 3, so the angle is 2 pi over 3. And if you kind of check where that is on our grid over here, 2 pi over 3 is certainly tangent to the curve at that point where the radius length is 0. So therefore, that sort of makes sense according to the graph. Depending on how accurately we sketch it, we should be able to use that as a guideline. Okay, so I think we're ready to go then. The area would be 2 times, right? Because we want to double this because we're doing our symmetry here. 2 times 1/2. Theta 1 is 2 pi over 3 to pi. And then we're going to multiply that by 1, or take the integral of 1 plus 2 cos theta squared d theta. Okay. So of course our 2 times 1/2 cancel out to leave you with a 1 out there. So therefore we're taking the integral from 2 pi over 3 to pi of, if we expand this, 1 plus 4 cos theta plus 4 cosine squared theta. And as we'll commonly see within these integrals that we're finding with polar area, is we'll oftentimes be faced with something like cosine squared or sine squared on the inside. So therefore, we want to make that double angle replacement. We know that this is going to turn into 4 times 1 plus cos 2 theta over 2 d theta. So this is going to be a 2 on the outside. All right, when all said and done, we're just about ready to integrate here. I'm going to combine a little bit more with like terms before I do so, because if I distribute that 2 in, 2 plus the 1 out front is a 3 plus 4 cos theta, plus when I distribute the 2 over here, it's going to be 2 cos 2 theta with respect to theta. Okay, so we're pretty close. It's a good thing I'm running out of space. All right, so if I take the integral, we're going to get that this equals 3 theta plus 4 sine theta, plus when I take the integral of cos 2 theta, it's going to be sine 2 theta divided by 2 with the 2 out front. That would cancel with the 2 in the bottom, so that just becomes sine 2 theta, which is kind of nice. And then we're integrating here from an upper bound of pi to a lower bound of 2 pi over 3. So when I plug in the pi's, what happens is we get 3 pi Sine of pi is 0. Sine of 2 pi is also 0. So that all kind of goes away. Minus, let's see what happens. When I plug in 2 pi over 3, that's going to be, the 3's cancel, so that's a 2 pi now. Plus, let's see, sine of 2 pi over 3, that's going to be sine of an angle in quadrant 2, which is positive. Remember, if I come back up here, sine would be opposite over hypotenuse. So that's radical 3 over 2. 4 times that is going to be 2 radical 3. So a little bit of special triangles there to get this answer of 2 radical 3. And then over here, it's going to be sine of 4 pi over 3 when I double the 2 pi over 3. 4 pi over 3 is the same triangle, but it's down in this quadrant. So now the opposite over hypotenuse would be negative radical 3 over 2. Okay. And if I clean everything up here, 3 pi minus 2 pi is just pi. And then if I get a common denominator here, this would be 4 radical 3 over 2 minus radical 3 over 2 is 3 radical 3 over 2. And we're subtracting that. So the exact area within that small loop of the loop in a loop that we started with is pi minus 3 radical 3 over 2 square units. Okay, so some of the trig evaluating at the end, just make sure you're confident with that and we can get there pretty easily. If not, you might just have to practice a little bit more with special triangles and things of that nature. But the hardest part was just remembering how do we get those bounds of integration to start. But then from there, you're going to see this type of process, especially, like I said, replacing cos squared is a very common replacement that we'll make. Okay, sine squared we also use with the same type of replacement there. Okay. All right, let's try another one like this. So on the next page, we have find the area of the region outside the cardioid, r equals 2 times 1 minus cos theta, and inside the circle, r equals negative 6 cos theta. Okay. So if you have r equals 2 minus 2 cos theta, which is what that really equals, this is a cardioid, that nice little heart shape with a width of 2, and the max r value of 4 is going to go to the left. Okay, negative cos has its max at pi. So you're going to go out 1, 2, 3, 4. There's the max. Width of 2. I'm using a scale of, by the way, the radius length of 1. Each circle is 1 radius length. Okay, so I'm going back to kind of a normal scaling here. So the cardioid would look something like this. Oops, I missed that max point. Okay. Let's just make it a little bit bigger. There, it counts. All right, so now that I have that sketch, I also want to sketch the circle r equals negative 6 cos theta. So in thinking about the circle, this is the diameter length, and the negative cos part indicates the direction that the diameter would go 6 to the left from the pole. Okay, so with that diameter of 6, if you can approximate a circle with that diameter, you get something that looks like this. Okay, and just try and be as accurate as you can with that sketch. And what we're looking for is, now that I have the cardioid sketched with the circle, we want the area of the region outside of the cardioid, but inside the circle. So hopefully you can see that that's this region here. And shade all of this in. Okay. So what do we want to find? We want to find that shaded region. So in order to find that, we could find the area from here to here. Okay. Or what we can do is we can double according to the symmetry again, right? So if we take the area of the circle minus the area of the cardioid, and then double from here to here along these bounds right here, okay, that region's area doubled would get me the total area that we're looking for. All right, so where do these two intersect? I see where I've marked it off. I mean, I don't want you to trust that that's exactly 2 pi over 3, but you know, how can I tell where these two intersect? Well, if we do 2 minus 2 cos theta equals negative 6 cos theta, we can solve this equation for theta and find out what angle makes that a true statement. So if I add 6 cos theta over here, we get 4 cos theta, subtract the 2 to here, 4 cos theta equals negative 2, and therefore cosine theta equals negative a half. Okay. The two values for theta here, it's the same exact reference triangle that we drew in the last example. So take a look back at it if you need to. It would be 2 pi over 3 and 4 pi over 3. Okay, so that would be these 2 points right here. I'm just going to use 2 pi over 3 as kind of the lower bound of integration. The upper limit I'm going to choose to be at pi. So according to symmetry, if we do 2 times the circle minus the cardioid area along these limits from 2 pi over 3 to pi, that's going to get me the desired orange shaded region, or orange, depending on where you come from in New York State. So, all right, now that I have that all set up, the area would be, again, double the 1/2 on the outside, so we know what's going to happen there. Area from 2 pi over 3 to pi of the circle, which is -6 cos theta squared, minus the cardioid 2 times 1 minus cos theta squared. And this is all with respect to theta. Okay. So now it's all about the simplifying from here. The hardest part, I think, in a lot of these will be just the initial setup. As long as we're careful with the algebra, hopefully evaluating in the end will go smoothly for us. So 2 times 1/2, now that's a 1 out front. We got 2 pi over 3 to pi. Let's see, -6 cos theta squared is 36 cos squared. And then we're going to have a minus, let's see, 2 squared is going to be a 4 out in front of squaring this binomial 1 minus 2 cos theta plus cosine squared. So again, that's all d theta. Okay, keep cleaning things up here. 36 cos squared, we're going to have a -4 cos squared here. So that's going to leave you with 32 cosine squareds. Okay, and then we're going to have a +8 cos theta. If I distribute the -4 here, -4. And just like we saw in the last example, we're going to wind up replacing cos squared with 1 plus cos 2 theta over 2. Okay, so when I make that replacement 1 plus cos 2 theta over 2, the 2 would go into 32 16 times. So if I distribute that to 1 plus cos 2 theta, we get 16 plus 16 cos 2 theta plus 8 cos theta minus 4. So hopefully you're okay with that step in your head there. Again, the 2 down here would cancel with that to get that 16, which got distributed to 1 plus cos 2 theta. Finally, we're kind of at the step where we can integrate. Just keep in mind that these would combine as a constant. 16 minus 4 is 12. So the integral there would be 12 theta. This is going to be sine 2 theta over 2. So now we get +8 sine 2 theta. And then +8 sine theta over here. Okay. So finally, integrating along our bounds from 2 pi over 3 to pi. We've already doubled it from the start. So this would be the final area here. We're going to have a 12 pi. These become 0 when you plug in pi there, just like earlier. Minus 12 times 2 pi over 3. It's going to be a total of 8 pi. Plus 8 sine of 4 pi over 3. So sine of 4 pi over 3 is negative radical 3 over 2. Times 8 is going to be a negative 4 radical 3. And then sine of 2 pi over 3 is going to be radical 3 over 2. So then it becomes plus 4 radical 3 there. Those wind up canceling pretty nicely to give you 12 pi minus 8 pi for a total area of 4 pi. Okay, so the longest part about this is once we decide the bounds of integration, we have the picture set up, then there are a lot of simplifying steps along the way to eventually get to this stage where we can take the definite integral. Okay. So what I'm going to encourage you to do for the last example, which is actually the same exact polar equations, is maybe just set yourself up. Okay, we'll go over this one in class. But can you recreate the picture? And when you redraw the picture, keep in mind that we're finding a different area in this one. It says find the area of the region common to the 2 regions bounded by these curves. So see if you can understand what that language means and shade the region. If you're a little nervous about shading the region because you don't want to have to go back and erase anything, then go ahead and leave that blank for now. But at least recreate the picture here. We'll go over this one in class tomorrow just to make sure that we're on the right track. And as soon as we're done going over this example, we'll take a look at one practice AP question from the good old year 1984. A lot of the questions lately have come from chapter 9 just to kind of keep us fresh with sequences and series. This one's actually throwing it way back. This is about related rates. So see what you remember about related rates here. But again, we can go over this in class. I will leave it up to you how much you'd like to attempt on that question. I'll give you a little bit of time next time we're together. Okay, that is it for today for shaded polar area. A little bit more with polar to come, and then we're right around the corner looking at our last unit on vectors. Have a great rest of your day.